Yes, so I'm Josh Junon. I'm going to talk a little bit about. Hold on. Let me get here. Yeah, that works. Okay, the Oro boot protocol, or doing a dance with undefined behavior. So Oro is an operating system project I've been working on for about 7 years now, on and off. If you were here at the last meetup, I did a lightning talk about kind of this, as well as a few other things regarding the project. Today I have a little bit more of a targeted talk, a little bit more specific. So like I said, my name is Josh Junon. I've been writing code since I was like 9, so that's, as of last week, 21 years now, yes, I think. I don't know, math's hard. I've been doing open source primarily in the Node.js community for a long time, about 15 years, and picked up Rust about 3 or 4 years ago. Seriously, I played with Rust maybe 10 years ago and have been kind of like keeping an eye on it since. So, but the Oro system, or the Oro operating system, the project is all written in Rust. Everything is in Rust. Doing a custom PCB, the firmware is in Rust. The daemon that runs some of the CI/CD stuff in Rust. So yeah. And today I'll be talking a little bit about the boot protocol, which if you don't know what that is, that's okay. I'll go through it. So yeah, I'll be talking about how kernels boot, what are boot protocols, the kernel boot protocol design constraints, so what I had to keep in mind when I was designing this, and how I used proc macros, procedural macros, to make it maintainable and understandable. And how I used a single line of code to deserialize those structures. So we'll be talking kind of like a serializer, creating a serializer with a proc macro, but in a way that a normal serializer serializes to like JSON, for example, and then you deserialize it back to some in-memory data structure. This serializer kind of cuts out the middleman and serializes one data structure to another one directly in memory. It's kind of a weird situation. It'll make more sense as we move on. There's a disclaimer here. This is a lot of information and a lot of development work condensed into a very tiny presentation. And I'm not going to go deep into the operating system development theory because it is a whole ocean of information. So if you know better than what's on the slides, that's great. I'd love to talk to you, but it's probably not going to be as comprehensive here as some of you might know. So just keep that in mind. And also, if there's something you see up here that you don't understand, it's probably not super relevant, so don't panic. If you get anything out of this presentation, it's that proc macros are cool, and if you've never written one, I suggest you go try one, because they're really cool. Rust does have undefined behavior, contrary to what some people who don't write Rust think, or maybe some people who do, but it's typically confined to the unsafe blocks, right? Operating system development is hard, very hard, and you have weird things pretty much all the time that you have to deal with. Especially when trying to employ good software practices and architecture and design and layout and structure, et cetera. Yeah, so we'll go right into how does a kernel boot. And like I said, remember, this is a huge condensation of information. So first we'll talk about bootloaders and what they are. And if you're thinking you don't need a bootloader, you're right, okay? But a bootloader is a nice and easy little program that runs mostly after the computer starts up, and we'll talk a little bit more about that in a second. But they interact primarily with the BIOS or the UEFI, which is just a system that runs right when the CPU starts running. It's usually a chip on your motherboard. And they pass the information that the BIOS or UEFI provides to the kernel via some sort of protocol. Protocol in this case is just a set of data structures, typically. They implement, some of them implement multiple boot protocols. If you've ever heard of multi-boot or multi-boot 1 or 2, a lot of them support that. If you've heard of Grub, Grub supports many different types of boot protocols, right? And they often have lots of helpful features for the user. It's not necessarily useful for the operating system developer or the kernel developer, but they're helpful for the user. Boot menus, if you have multiple operating systems installed, you can switch between them. They can also do things like pulling from a web server if you really wanted them to. They could pull from weird different places on your computer, different devices. They can do a whole bunch of stuff, right? But their main primary goal is to boot the kernel, to get you from how it started, the electrons are starting to move through the machine, to your kernel's execution, right? And they also simplify writing a kernel. If you've ever gone down the path of writing a kernel, just as a toy project, and you look at like how to make a bootloader, that's almost its own field of computer science in itself. And so bootloaders that are already written for you make writing a kernel, even a basic kernel, very simple, right? So that's what a bootloader is, just as we move forward. Here are common bootloaders that exist. You might notice some of them. I won't go into any of them right now. The most common ones are Grub. The one that I target is Lamine, and Pixie is notable. It's not really a bootloader, but it's if you have to flash Windows onto 1,000 machines in an enterprise setting, you're most likely using Pixie, right? It's just like a network boot protocol. And there's all these other ones. They all do their own system initialization and their own functionality, and they have their own quirks and things like this. So there's a bunch of them out there, right? So what kind of information would a kernel need to know when it boots up? And there's a lot of information on this slide. I'm going to just touch on it just a little bit. The most important one, at least right now for the Oro project, is the memory map. So what physical memory exists for the computer, RAM slots or video buffers or things like this, what exists for the kernel to use and store bytes and things in, right? It needs to know that because it's not an inherent thing. You could have 256 gigs or 256 bytes. The kernel still needs to know, right? All sorts of other stuff. The kernel command line, just like a normal command line interface, you can also pass a command line to the kernel or to its modules. Some of you might have done this, mitigations for like Spectre and Meltdown. You can turn those off via the command line, things like that, right? You have ACPI. What does the power button do when you hit it? It's not the only function, but it's one of the functions. SMBIOS, what devices exist? In a nutshell, EFI tables, what devices exist? CPU information, how many CPUs are there, and can I use all of them, and are they economy, or are they high-powered, or whatever. And additional modules, so things to load along with the kernel to run, so additional drivers, things like this, and the current timestamp, which is what the little battery on your motherboard is for the most part, right? So these are kind of the things that a kernel might need to know when it boots up. So when you boot up a computer and you turn the power on, the first thing that runs is your BIOS or the UEFI. It's kind of like firmware for your motherboard. You can think of it that way. And it does a bunch of initialization steps, like making sure all the devices are working, find out what memory is good, what memory is bad, etc. It also has, if you've ever changed the boot order, I want to boot from this device or USB device or CD, back when CDs were a thing, which is crazy to think about. They're not a thing anymore. But when they were a thing, you could select, I want to boot from a CD. This is your BIOS, right? After the BIOS, again, if you're using a bootloader, it will hand off execution to the bootloader, which by itself is kind of like its own little kernel, right? It does some functionality on top of the BIOS. And in this case, in the vast majority of cases, a bootloader will simplify the information that comes from a BIOS or UEFI and will massage it in a way that's a little bit easier for kernels to use. It's one of the functions of a bootloader, right? And then from there, that information gets passed with multiple different kinds of data structures. These are called boot protocols. We'll talk more about them, to your kernel. And your kernel then takes that information and can use it to use the machine, right? Whatever that kernel needs to do, right? So this is a typical boot process. Like I said, a bootloader is optional. Sometimes the kernel can do all of this that you need it to do, but there's a lot of extra code, and like I said, there's a lot. There's a lot of weird stuff that has to happen in order to initialize a CPU for usage, right? So what is a boot protocol? So these are all boot protocols. If you've seen any of these before, we can kind of argue on like what really is a boot protocol, but for the most part, for the sake of this presentation, these are all boot protocols, right? Multi-boot 1, multi-boot 2, Lamine is the one that I use the most, and Pixie, or maybe there is no boot protocol, right? What is the problem with having so many different boot protocols? Is that it causes tight coupling in the kernel. So, for example, if we have multi-boot 1, multi-boot 2, Lamine, Pixie, and maybe 10 other ones that we want to support, the kernel otherwise has to know about all of them. So that means rebuilding the kernel every time you make a modification to one, or a bug report, or if you want to add one or remove one, whatever it is, you have to rebuild the kernel. And if you've done anything at scale, if you've worked with Linux at all, rebuilding things and redistributing them, especially something as touchy as a kernel, can cause a lot of problems. And so what is the solution other than to decouple these, right? We have this fancy thing that I made yesterday. So we have boot stages, which are in and of themselves kind of like tiny kernels with one specific purpose, which is to take one of those boot protocols and massage it into yet another boot protocol, that we can hand to our kernel, and that the kernel understands one boot protocol, and all of these translate between multi-boot 1, multi-boot 2, et cetera, to our kernel's boot protocol, right? So it's just one added layer. You can think of it as kind of an abstraction, right? So the important part, though, is that, oh yeah, we can also version them differently. This is another slide I made it. We can version them differently. We can install them, remove them, and we never have to rebuild the kernel. That's really the important part. We can add them, and it always stays decoupled, right? Important part. Really slow transitions, yes. There we go, kernel boot protocol. This is kind of the point, right? This is what have built already. And this is the reason why proc macro came in handy, because this stuff gets very tricky, very, very tricky. And we'll talk about why. But this is the important part. We decouple the boot stage from the kernel. You don't have to rebuild the kernel, right? So if we go back to our graph about the common pathway for boot, we go from this, the kernel knows everything kind of diagram, to this decoupled diagram, where there's these individual boot stages, and then there's one protocol between the boot stage and the kernel. So here's the boot protocol. This is the data structures that our kernel understands and only needs to understand, and yeah, these are all the other boot protocols that we can support, right? So let's look at what some of these data structures might look like. These are copied and pasted, these are real. This is from the mean, and this is just for a single memory map entry, meaning like one region of physical memory that we can use for storage, right? We have a base, which is a U64. In this case, it's a pointer. It's just a number. It's not really a pointer because you can't write to a physical address directly in most cases. A length, how many bytes long is it? Is it 2 gigabytes? Do you have a 2 gigabyte stick in there? And what kind of memory map is it? So what kind of region is it? Is it good memory? Is it bad memory? Is it reserved? Is it reserved for the bootloader? Can you reclaim it from the bootloader? The bootloader doesn't need it anymore after you exit, right? All these kinds of things the mean supports. The ORO structure, if you look, very similar. We have a base, a length, and a kind, but our kinds are a little bit simpler. I'm sure they'll get more in the future, but for now we just have usable. Is it a module, something that we need to hang on to, or is it reserved, meaning we can't use it, right? Is it bad memory or memory that belongs to ACPI or something like this? And a boot protocol just is the translation between this input protocol and our kernel's protocol. That's it. That's the whole idea. So there are many constraints when thinking about designing this thing, and it might not sound that interesting to you, but it gets really interesting when you consider that there are a lot of things different about this stage, this type of booting, or this type of code. We don't have the standard library. There is no standard library. We don't have a kernel. There's no threading. There's no I/O. There's no file system at all. There's nothing, right? So we have to operate within this no STD tag and no alloc. We have no heap allocator. You could technically have one, but it would be kind of hefty. We have to transform these data structures, and we have to allow variable length data. That's kind of the focus of the proc macro, right? If you have 150 sticks of RAM, but for some reason, because of memory constraints, we only allow 32 in our list because we have a fixed length list, that's 150 minus 32 sticks of RAM that our kernel is just never going to know about, that you'll never get to use, right? So we have to allow for variable length data, which if you've done any hardware programming or firmware programming, you know that variable length anything can become a problem pretty quick, right? So we have to understand how to serialize variable length stuff, arrays, lists, things like this. Another purpose is we have to serialize, or another constraint, we have to serialize to contiguous physical memory pages. I won't talk too much about that, but it was a constraint of the boot protocol. And we have to, at least for the ORO kernel says, I'm going to look for these data structures at a specific address in virtual memory when I boot up. That's how I know where they're at. If they're not there, I'm going to blow up. That's really the unsafe part of this, right? And it gets even more hairy in just a sec. But the kernel will look for these data structures somewhere in memory at a specific address. And we have to be able to write them at that address or make sure that they're there, right? And the last thing, for maintainability's sake, it needs to be clear and understandable. If you've ever, probably not, but if you've ever looked at a boot protocol in C from toy operating systems, the code is really, really hairy and messy. And it's a lot of manual memory management. I wanted to make it so that it was so easy to maintain that it was just like changing data structures and everything was just fine. Hence a proc macro serialization. You can kind of see where this is going. So this is where the hard part comes in, right? There is no kernel when we're in the boot stage. The kernel doesn't exist. It's not in memory. It's loaded in memory, but it's not It's not running. There's no I/O, there's no IPC, there's no network, there's no way to transfer this information in any way that we would normally transfer information between processes, right? And also, it lives in a completely different memory layout than the boot stage. And when I talk about memory layouts, I mean for the entire system, right? You can organize memory in an operating system however you want to, with a memory management unit. With most x86 machines, ARM machines, they have some way of organizing memory however you want. And the way that the memory that the bootloader sets up for us works is going to be different than what the kernel needs. And so you have to plan for this before the kernel ever loads. So it's a twofold problem, right? Yeah, I'm going through this already. I'm just going to speed through this really quick. So this is really technical slide, so take this in if you want, but don't be worried. But there's all these problems that you face that you wouldn't normally face when you're trying to just move data from one place to another and make it available for another process, right? So there's lots of problems with this. And really, it's the variable length stuff that really gets tricky. So when Lamine boots, Lamine is the first bootloader that I'm supporting because it's the easiest to work with, and there's nice Rust crates for it. And when Lamine boots, this is kind of the memory map of an x86 machine. It only guarantees that we're somewhere up in these higher addresses. All of this is undefined. You have no idea what's here, and you can't make any guarantees about the order of things or where things live in memory. You have no idea. You have to treat it as a black box, right? Versus the Oro kernel has a very specific memory layout that it requires and will enforce. And so it knows that the boot protocol is going to live here, right? It's at the very top of this blue block. That's where it's going to look for it when it boots up. So you have to make sure that you're not overwriting your own memory when you're writing memory for the kernel to use when it boots up. And you also have to make sure that wherever you're writing it in the current memory layout, it exists in the right spot in the target memory layout. So the problem is twofold. We're transferring data from one format to another, right, from Lamine's to ours, and we also have to make sure it's put in the right spot. So it's two problems at once, right? So now we're going to use proc macros to do this, or we do use proc macros to do this, or to help us do this. So I wrote a proc macro serializer called certamem, serialized memory. Not a very imaginative name, but it works. And it serializes Rust objects to other Rust objects in memory. It's not that interesting at face value, but when you look at, when you think about, how do I serialize an iterator or an array and transform it without allocating on the heap, and also I have to make sure all of the pointers and everything match up, you can start to see how it gets hairy, right? So here's what the boot protocol looks like in the source code. This is the source you're writing, right? So you can see our derive macro up here, certamem, certamem, certamem. And everything looks pretty bog standard until you get down to this memory map. And this memory map, sorry for the people who are in the back, this memory map is a stack-based owned iterator. So we can allocate these iterators and create them on the stack, and these iterators will transform our variable length data on the fly and serialize it on the fly as the iterator is iterated, as it's consumed, right? So here's what gets generated. This is a call to cargo expand. If you've never used cargo expand and you're doing proc macros, you should really check it out. Cargo expand dumps out the source code of your program after all of the macros have been evaluated. So this is the output of the derived structs, the certamem derived structs after everything has been evaluated. And you can see our memory map down here has gone from an iterator to this really crazy type that we'll talk about in just a second. So this is what that type looks like, and it looks very much like a C++ error. But I'll simplify it for you. It's really this, right? This is really what it is after all of the type extraction has happened. So it's just a statically allocated slice of memory region proxies. A proxy in this case is a generated type, right? So certamem generates a second type that converts all of the iterators to these slices, right, with some fancy type extraction, but really this is it. Okay, so this is what the kernel will use. And what we saw before is what the source code uses, what the boot stage uses. So the boot stage hands it an iterator, and then the kernel gets back a statically allocated slice of objects that it can use, that are in its data structure that it understands. So this is how the boot stage would use the protocol. So it initializes everything, like these magic nonce and nonce XOR magic. These are all bog standard. They're just copyable numbers, nothing really special. But here's where it creates this iterator, right? And so we map the memory map from Lamine. And for every object, or for every Lamine region, we create a new Oro boot protocol memory region. And like I said, it's very much similar. The only really special thing here is we figure out what kind of memory region we want to tell the kernel about, right? So that's how the iterator works. That's very simple. But in order to do the benefit of this is that we don't have to allocate anything on the heap. We don't have to pre-transform this and store it in memory somewhere and then hand it to the kernel. We can do it on the fly, and the serializer will handle serializing it on the fly as well. So we hand that an iterator, and then this is what gets generated from Certimem. So this is the generated serialization method. And this is a lot, so we'll kind of go through it really quick. So we have our layout. So if you're not familiar with layouts, a layout is kind of like size of in C, but it also has a line of it from Z, kind of the same things. And a layout is just how big is something and what is the alignment. If you don't know what alignment, that's okay. Alignment is just this thing has to start on this byte boundary. So if it's aligned to 4 bytes, it means that the ending of the address at which it starts is neatly divisible by 4. That's alignment, right? And it's a requirement by CPUs and chips and processors and all sorts of stuff, right? So a layout includes that information. We allocate that much memory that we need, and then we serialize each of those very simple fields normally. But then we have this memory mapped, this iterator thing, and we have this function called serialize iterator to slice. And this is kind of where the undefined behavior can start if you're not careful. So serialize iterator to slice. We take the count, so we clone the iterators. You can clone iterators. We take the count first, and then we create a new layout. We create a new layout of an array. So Rust also has layouts of arrays. You can actually create a full layout of an array if you know how many elements there are, and you get all of the proper alignment, right? So this is a real requirement of keeping things well defined in Rust. So we take the count, we create an array from it, and now we know exactly how many bytes and what the alignment is that we need to allocate and align to. And then we use this core. If you're not familiar with core is like the standard library light. It's the stuff that can be implemented safely across pretty much any architecture, and a lot of what's in core is just re-exported by the standard library. So iterators, println, not printf, println, and a bunch of other cool things that you might already normally use, they typically actually live in core. They're much lower level. Anything that isn't I/O or anything like this is in core. And you can use core in no standard, in firmware, in kernels and things like this very easily. And one of those functions is working, or one of those modules is working with slices. So you can create a slice from a base pointer and a length. And as long as the slice knows what type you're creating, it can create everything that you need very readily for you and give you back a normal Rust slice, right, which has length information in it. But slices have lots of undefined behavior with them if you don't do them correctly. And we'll talk about what that undefined behavior is, but you can get into hot water real quick. So we create a slice from that base pointer of the variable length array of things that we're building. I have no idea why it's doing this, sorry. And then the number, and then we allocate that memory, and then we serialize each of those items to it, and then we return the slice, right? That's all this does. So why is this dangerous? Because slices that we generate are not valid until the kernel can use them. They're not pointing to valid memory half the time, or most of the time. There's no guarantee that they're pointing to the right memory. The pointers that we generate that have to be allocated, that we write to in the boot stage, are valid. But when we also write the pointers that live in this is the hard part to explain, so bear with me. If we have 2 pointers we're working with. We have a pointer that lives in the kernel, in the boot stage, right? That's the one that we can write to. That's valid. That's fine. But we also have a pointer that the kernel needs to use eventually. And remember, the kernel and the boot stage have completely different memory layouts. So that memory is the same. It's backed by the same physical page. It's the same RAM. It's the same bytes, but it's mapped to a different place in memory. And that pointer has to be valid when we switch to the kernel, right? Or else it's undefined behavior, or else you'll just get garbage back, or you might get a seg fault, or if you have seg faults, it can get very complicated, right? So if we're not careful about how we use these slices, we can incur undefined behavior, and the guarantees that Rust give you in normally safe code fly out the window, right? So there's a whole section on what's valid for Rust slices. I'm going to talk briefly about these, but these are in the docs. If you go to the slice module, you can read this yourself. First, the data must be valid for both reads and writes. We make sure that that's the case in both the boot stage and the kernel, because we don't deserialize invalid pointers in the boot stage, and when the kernel boots, all of the pointers are magically valid, right? The entire memory range of this slice must be contained within a single allocated object. Well, we do that because we use Rust's provided array layouts, right? So we know that that's the case. Data must be non-null and aligned. Yes, we do that. We align everything. Data must point to length consecutive property values. Yes, of course we do that. And the memory referenced by, this is really the important one, the memory referenced by the return slice must not be accessed through any other pointer. That means you cannot have two slices that point to the same or overlap to the same memory region at all. That is a guarantee that Rust makes, right? So we have to be very careful about that. What's that? If they're mutable, it could be. I honestly don't know. I think it's also if they're immutable. It could be the case. If the data structure, if the data types underlying, there's no aliasing. So if the data types that you're pointing to are aligned, you can have slices talking to the same parts of memory, but they can't talk if they does that make sense? If they overlap. So I can't have a data structure that's 10 bytes long, and the first element of a slice points to the beginning of that 10 bytes, and then another slice points to the 5th byte, right? Because then the types don't match, right? Because a slice has to be contiguous bytes. So you can't have a slice of things that are inside of other slices, right? You have to be very careful with it. With mutable, yes, definitely. But there's still some caveats you have to run into. So we have to make sure all of these invariants and these assertions that Rust dictates remain true, and we're really playing with fire here, right? Yeah, like I said, we're playing with fire here. So it can get very, very tricky, very fast. So what is the takeaway with all of this? If I've lost you, that's totally okay. The whole takeaway here is that using proc macros allowed me to do this in a way that as long as the proc macro is working fine, then I can modify the boot protocol and its data structures however I want, and I don't have to worry about this anymore, and it's just a cool thing I wanted to tell you about. Because proc macros are cool, and if you haven't played with them, then I suggest you do it, because they make a lot of things really fun. So, we talked about serializing to memory, right? But how do you deserialize from memory? And this is what I was talking about before. There is no deserialization. You just cast the base pointer to a reference, and it just works. This is what the kernel does. So it knows where these boot protocols live. You cast that base protocol to a pointer of that type and return a reference, and everything is still well defined. And that's it. If you want to follow the project, if you have more questions, please ask. But yes, this is the link to the kernel. And for your attention, here's a parrot text. This is my parrot Lucky. Yeah, come follow the project, follow me. Thanks. This is the next engineering problem. There we go. Good, thanks, yes? Questions? Oh yeah, questions.
There.
Yes.
So the transformation that you were showing us from like data structure to data structure, that happens at the boot stage, right? And you're creating slices at the boot stage, right?
Yes, correct. Yeah, the boot stage is like a little tiny kernel that does, its only function is to translate from what the bootloader, the data the bootloader gives you, to a format that your kernel can use. That is a boot stage, yes.
And so you're creating slices and you get an address, right?
Yeah.
That's in the memory layout of the boot stage.
Correct.
Not to the kernel.
Correct.
How do you transfer that?
So you,
the kernel will see.
yeah, so you, there's several ways you could do it. The way that Lamines does it, so when Lamine boots, you can tell it to map all physical memory into what's called a direct map. And a direct map is where, let's say, the first physical range of memory you can write to is at byte 1000, right? And so Lamine will give you a base pointer, let's call it 5000, right? And it'll say all of the memory is mapped one-to-one with all of the offsets starting at 5000. So if you need to write to a physical location that the memory map gives you, you add that address to the offset, right? So for example, that first memory region at 1000, you would add to the offset 5000, and when you write at memory address 6000, you're really writing at the first byte of the first physical range, right? This is called a direct map. It's not the best way to do things in all cases, but that's what we're using. And so if you know how to write to the physical memory using an offset, it's called an offset map, then you can construct a valid pointer and thus a valid slice to write to for the boot stage, but then also recalculate where that will be when the kernel boots and create a slice from that, and you write that slice to the data structure. You don't use it when you're constructing all of this stuff, when you're serializing, but you write that slice so that when the kernel goes to use it, it's then valid. That's how it works. And that's why it gets complicated. Yeah. Yes?
I mean, I don't know a lot about kernels and booting and all that stuff.
Yeah.
But what you just said with the offset, is that then like the singular information that is passed from the bootloader to what you're actually booting with the kernel?
No, that's not passed.
Is there any other communication happening between the bootloader and the kernel?
Nope.
It just knows which where it's from.
There are technically other ways you could pass stuff to the kernel, but you typically wouldn't. You really only have memory. There's, like I said, there's no I/O or anything. You have to put the memory, you have to put the data somewhere that the kernel can pick it up, but the kernel doesn't exist. It's like trying to have a call with someone who you're about to call and telling them everything about your day, but you haven't called them yet. And then when you call them, they have to magically know how to listen to what you just said. Like it becomes very tricky, right? So the best way to do this is within memory, because when you go from stage to stage to stage, the memory doesn't get wiped. Nothing like resets your RAM, right? So you can guarantee that that data is still there when the kernel boots. Yeah. Go ahead.
Do you support other architectures than x86?
At the moment, no. Right now it's only x64, but ARM is the next one up at some point. Will be supported, yes. I'm not an ARM expert. I know a little bit about it, but I have someone who will do the ARM port at some point. They said they would happily do it. So, yes, it's in the plans. Any other questions?
Yeah. So is there any difference as far as the operating system is concerned between bootloaders that that are able to load like one single stage such as Lilo versus like Grub, which I know like, used to have like the initial bootloader and then it would load another another section after that because it wasn't able to all fit inside the master boot record. I don't know what it's doing now, but like is there any difference as far as the operating system is concerned between I guess different implementations would make like multiple stages of the bootloader and how that might handle memory and
If I understand your question correctly, is there a difference between how operating systems handle different bootloaders booting from like old like master boot record and things like this?
Yeah.
I can kind of answer generally because that's a whole conversation on its own. So what you're describing is called chain loading. And chain loading is where you chain load different bootloaders together or boot stages together. And yeah, the classical way was the master boot record, which was only like, correct me if I'm wrong, it's like 512 bytes. And you have to have the entire boot process in that 512 bytes. And then you can chain load to something that loads things from the disk and you have more memory to work with, right? In terms of operating systems, some handle it directly, some don't. I know that Linux can, or at least could at one point in time do this. I honestly don't know what the consensus is now. Right now, Oro does not. I don't want to try to fit anything into 512 bytes. So at the moment, it doesn't do that. But it's a good question. Anything else? Yeah. Oh, sorry.
Yeah, I used to teach operating systems, and it's customary to use C for representing concepts and stuff like that. Do you think that Rust can be a good choice for that?
Yes, and also I won't go back now because everything's just not working. But it is repr C. All of the boot protocol structs are in C representation. So in theory, you could do this from C. Would I recommend using Rust like without using a C representation at the moment? No, because Rust's ABI is not standardized yet. Correct me if I'm wrong, but that's still been like an ongoing thing for years and years and years. It's not standardized yet, so no, I would not recommend it if you want anyone else to use your bootloader or your kernel other than you. So at some point, I hope so. But for now, if you slap RepRC on it and you understand some of the caveats with it, like how enums work and things like this, then you can probably reason about it fine. I think it's fine. What I would love to see, if someone knows about this, is generating C headers from Rust data types. If you know about that, come tell me, because I would love to know. But aside from that, it should exist. Yeah, I don't know yet. So, but things like that would make it easier. But writing data structures in Rust that are usable from C, I think would work with RepRC. At least these are written to be compatible. Yeah.
Yeah, I also like follow 60%, 65% maybe, but like it's pretty exciting, and I want to ask a general question, like in terms of like because your general goal was to maintainability and simplicity, right? In an area where you don't find maintainability and simplicity. So, what have you, or did you sacrifice anything to achieve that in terms of functionality that we don't follow and see right now?
Sanity and sobriety. Yeah. Yeah. So the question was, did I sacrifice anything in order to achieve maintainability and clarity? With this
personally.
Not personally. With this, yeah, I mean, so when I say maintainable and understandable, I'm not talking about the proc macro implementation. If you go look at proc macro anything, that stuff is crazy, nasty, not fun to read and debug. It's like reading a templating language in Rust, written in Rust, using Rust and generating Rust. It's a nightmare. But the end result is that people who look at how do I interface with this kernel should be maintainable and easy, and I think I've achieved that at the expense of, proc macros are super not fun to look at. In fact, I was doing this presentation and caught something that really made my eyebrow raise, and I had to go back and look at my own code that I wrote just a couple of months ago and figure out what the hell is going on here. So it can get very complex. So there is that trade-off for sure. But the benefit here is that generating this unsafe stuff in a way where you can at least have some control that the unsafe stuff is reproducibly safe, or you know what I mean? Like you can audit it and it's generated and it reduces the surface area. It's a huge win, I think. So it's a necessary trade-off. Yeah.
So I think one thing you touched on it now, right? Like proc macros, you can use them to simplify generation code, right? But they tend to be very monstrous, right?
Yeah.
You're hiding the nastiness in there.
Yeah.
So a question for you is like, are you writing tests for these things? Like,
No. No. Well, actually, serious answer. Am I writing tests? I'm doing more than writing tests. This is probably, if we do another Rust meetup, I want to talk about this. This was the other potential topic. I'm building a CI/CD pipeline for testing the kernel, and built my own custom PCB from scratch to do this with GitHub Actions and running everything through Pixie Boot onto a real machine. So if you want to talk about that, happy to talk about that as well. But CI/CD is really important for the kernel. The proc macro stuff, not so much. I can verify with my own eyes that it's doing what it's doing, and then if you have tests for the thing that it generates, it's good enough for now. If someone wants to write tests for the proc macro stuff, they're welcome to, but at this point there's so much. Operating systems development is not just a mountain, it's like a planet. It's like building everything from the ground up, and there's so much work to do that you have to make some time sacrifices. So no, there's no tests. That shouldn't come as a surprise to anyone, but there is testing in the pipeline for the kernel itself, not so much the proc macros. Yeah. Yeah.
One last question.
Sure.
You made it pretty much this is a trade-off, right? Trade-off how simple the kernel is,
Yeah.
how simple the proc macro is, how simple the bootloader is.
Yeah.
And you made the trade-off that the kernel should be simple.
Yeah.
Right? And moving all the complexity to the proc macro to the bootloader. And the question was, what's the overall complexity now of the thing? Right? Does it increase, or would it be? For me, it looked like the Lemine bootloader is just too complex there, right? You could remove that. You could remove.
Yeah.
Go back to your master boot record. Load your stuff in memory and done. Right?
Yeah.
So it's.
Yes. But the bootloader does a lot more than just transformation. So I didn't really touch too much into it, but the bootloader does a lot of probing of devices, things that's not standard, things that could be dangerous if you don't do them correctly. To see if a page of memory is writable, you don't know if that memory is RAM or if it's going to a control system for a flamethrower, right? So bootloaders have other things that they need to do, and really the topic of complexity is, for me, it's more about responsibility. What should things do? And in the case of the kernel doing all of this itself, it adds a lot of complexity, I think, that I can offload, at least for now. Especially in the early days of development, I don't want to be dealing with moving the x86 kernel or CPU into protected mode versus real mode. I don't want to be having to. I know it's not a lot, but there's still non-trivial stuff, right?
It's one page of code. So
Yes, but there's still a decoupling aspect of it, right? And an interface, interoperability. I want the kernel to be callable by other things, even if I didn't write it, right? So it's more of a design. It's like a design approach versus like a practical approach. Yes, I could do all of this myself. I could do the serialization myself, but there's a lot of benefit in knowing that I can change these data structures, not have to worry about did I copy and paste the serialization stuff correctly, right? So that's kind of the approach I took. Plus, I just like writing proc macros, which I don't think is.
what's the overall time frame?
For the proc macro in particular, I think I wrote in like 2 days. So not a huge time sink, but for me, it's kind of a big time sink. So yeah, cool. Thanks everyone.
All right, thank you.